Alright folks, so welcome back. We're gonna start now learning vectors and how to write vectors in Matlab. So vectors are basically a one-dimensional array. This vector or any vector can be written as a row vector or a column vector. So let me show you how we can write a row vector. So I'm gonna come to Matlab. So let's call a vector A. I will come to the command window and I will write A, and this will equal to. One way to create a vector is to open a bracket. That means start a vector, and now I'm gonna enter the first index, which is 1. Then I will have space, and then I will write 2. Then I will have space and I will write 3, and I will have space, I can write 5. Now I will end the vector by having a closed bracket. So the closed bracket says that this is a vector. I'm gonna put a semicolon so that the vector will not be echoed. And then I will hit enter. So you can see, if you come to the workspace over here, you can see that there is a variable called A, and then you can see the value. It says that it is 1, 2, 3, 4, 5. The minimum value is 1 and the maximum value is 5. So the workspace window here shows you what kind of variables we have declared in the command window, and here we have the variable A. Now if I want to echo this vector, all what I do is I write A, and you can see that I have declared a row vector, and the row vector is basically a one-dimensional array that reads 1, 2, 3, 5. So this is a row vector because this vector is a row. Now I can declare a column vector. So let's say that B is a column vector, and I will say that this column vector equals to. Now I will open a bracket. That means start entering the values for that vector, and I will say the first index value is minus 1.4. I will move to the next row because it is a column vector, so I will have a semicolon, and then I will say 2.5, and then I will have a semicolon, and then I will say minus 7, and this is a 3 indexes, or the dimension of this column vector is 3 values. So I will have a bracket, a closed bracket, and this closed bracket says the end of the column vector. So let's look at the column vector. I do not have a semicolon here, so I wanted to echo this vector. So when I hit enter, that's what I get, right? So the value have been echoed as it is shown here. So basically you can write vectors as row vectors or column vectors, and I can use the transpose complex conjugate, that's called the Hermitian transpose, to convert between column and row vectors. So for example, I can say that C will equal to the transpose of B. So the way I will do that is I will say it will equal to B, and then I will use this apostrophe sign, and that means give me the transpose of B. So B was a column vector. When you get the transpose of B, you will get a row vector. So now you end up with a row vector. So this is a very exciting way of dealing with vectors, and you can convert the vectors between rows and columns. So for example, I can say that D will equal to A. apostrophe, that means the transpose with a complex conjugate. I will show you that shortly. But if you do that, we know that A was a row vector. Now when we get the transpose of A, it will give us a column vector. Now vectors can also take complex values. So let's say that the vector E will equal to, and then I will write a complex vector. So the first element will be 1 plus 2j. The second element will be 2 minus 5j. And the third element will be minus 3.5 plus 3.4j. Now I'm going to close the vector, and when I hit enter, so you can see that this row vector is a complex value. Now I'm going to say that f will equal to E Hermitian, and the Hermitian, remember that it will do the transpose and it will give you the complex conjugate of that value. So when you do that, you will see that you get the complex conjugate. The first element, oops, sorry, let's go back down. So you can see that the first element was 1 plus 2j. Now it becomes 1 minus 2j or 2i. Over here we have 2 minus 5i, and then it becomes 2 plus 5i. Here it was minus 3.5 plus 3.4i. Now it is minus 3.5 minus 3.4j. So clearly that when you use this apostrophe sign, it does the transpose plus it gives you the complex conjugate. This is called the Hermitian transpose. Those are vectors, and that's the transpose of the vectors. And now we wanted to see what's another way to create a vector. There is another way to create a vector, which what we call sequential vector. Sequential vectors are very important in plots. So we're going to learn how to do plots once we get over the vectors. But let me show you how we do sequential vectors. So let's say, for example, I wanted to say the vector h, will equal to, I'm going to give a sequence from 0 to 10, and I want this vector to be incremented by 1. So how can I do that? I will say 0 colon, the increment is 1, then I will have a colon that's 10. So here it says that it is a vector, will start at value 0, the increment is 1, and the final value is 10. So when you hit enter, what we have is 0, 1, 2, 3, 4, 5, 6, all the way to 10. See, and this is very nice because now I can create a vector in sequential order. It doesn't have to be increments of 1. It can be increment of 0.1, for example, or any other increment value. So let me show you another vector where I will say vector I will equal to, let's say we will start from minus 0.5, and the increment is 0.1, and then it will end at 0.2. So from minus 0.5, the increment is 0.1, and the final value is 0.2. So over here I will have 8 values, and you can see that I start with minus 0.5, minus 0.4, because the increment is 0.1, right? So, and then I have 0.3, 0.2, 0.1, then 0. Now I move to positive 0.1 and positive 0.2. So I start all the way from negative 0.5 all the way to positive 0.2. And this becomes handy when it comes to plotting functions. As I said, we will show you that shortly. But there is other more important stuff that we need to do with vectors before we move to plots. One of them is how can we do vectors in arithmetic operations? How can we use vectors in arithmetic operations? So let me clear everything so far to make things look nicer. So now what I have is a clear screen, and now we are ready to learn arithmetics with vectors. So let me declare a new vector, which is a will equal to open bracket 1, 2, 3, and 5, like we did earlier. I'm gonna put a semicolon, which means do not echo. Now I want to add a scalar to each value in that vector. So what I will do is I will say vector b will equal to, and then I will say a plus a scalar which is 3.5. And let's hit enter and see what we get. Over here we are saying that add 3.5 to each index within A. So what we will end up with is B will equal to 4.5. That's the first element, because 1 plus 3.5 will give me 4.5. The second element will be 2 plus 3.5, and that will be 5.5. And the thing continues all the way until the last element, which is 5 plus 3.5, and that is 8.5. The key idea here is that I can add a scalar to a vector to each element within the vector. Matlab will allow us to do that. Basically, you add a scalar to that vector, and it doesn't matter which one I will write first. So let me show you another example with subtraction. As you know, subtraction is just another form of addition. So let's say that C will equal to 3.5 minus A. So now we are doing subtraction by scalar of 3.5. And you can see that when you do the subtraction, you get minus 3.5 from each index in the vector A. You can also apply the same thing to a column vector. I'm not going to do that to save time, but if you have a column vector, you can also add or subtract scalars from each element in that vector. There is also multiplication and division by scalars. So let's say that we have vector D will equal to vector A times 2. So this will double vector A for us, and let's see that. Indeed, it doubled vector A because I multiplied A by a scalar 2. That means that each element in A is multiplied by scalar 2. I can divide also, so I can say that vector E will equal to A divide 3.4. And you get here a division by scalar operation, where you start to have each value within A is divided by this scalar value, which is 3.4. So far we have learned how to declare vectors as row and columns, and then we learned how to do the transpose with a complex conjugate to a vector. So far also we have learned how to do scalar arithmetics on a vector. So what we're going to do next is we are going to declare how we are going to do something we call index operation. So index operation is a very important operation for us in a vector. So let me also clear the window, and then let me also clear the workspace, and then also let me clear the command history. And now I'm interested in something that is new for us, which is called index operation. Index operation is very powerful in Matlab, and let's define it very clearly. Let's say that I will define a vector A to have 3 elements, 1, 2, and 5, and I'm not going to echo it, so I will have a semicolon, and then I will have vector B to equal to 2, 1, and 5, and I'm not going to also echo it, so I will have a semicolon. So what's in an index operation says that is I will apply the first index in A to the first index in B, the second index of A to the second index of B, and the third index of A to the third index of B. Right? So to do something we call index operation, the size of the vector A must be equal to the size of vector B. So the two sizes are equal, and this is very important thing for us to have. The second thing I want to do now is I want to define index operation, so I will do something called index multiplication. So C will equal to the result of this operation. The index multiplication is going to be stored in vector C, and that will be A multiplied by, as index, so I will say a period multiplied. So this says index operation. The period here says it's an index operation, and then I will have times B. And let's see what we will get. So what we will have is basically the first index of A multiplied by the first index of B. So 1 times 2 is 2. And then the second index of A multiplied by the second index of B. So 2 times 1 is 2. And finally we have the third index of A multiplied by the third index of B, and that will give us 25. The key idea here is when you have a period before the multiplication, that means you multiply each index in A by each index in B. If you say that C will equal to A times B, if you do this operation, you will have an error. The reason is Matlab will understand that this is as a matrix, A as a matrix and B as a matrix, and to do a matrix multiplication, the dimensions of A and B must be valid for a matrix multiplication operation. But they aren't here. The two vectors, they cannot do the multiplication like that, and you will have an error even though they have the same size. So let me show you that. You see, it says error. It says enter matrix dimension must agree. So we don't have agreement on the matrix dimensions, and that's why you have an error. So what I will do is I will go back and I will do an index multiplication like I did before, and that's what we have here. Index multiplication is very powerful for us to use when we use Matlab, and you will be able to do it very fast. As you get familiar with Matlab, this becomes a very handy tool to use. So what we can do next is that we can also use index division. So let me show you that by writing a new vector. We're going to call it D, and that will equal to A, and then we're going to say index division. So we will have a period backslash, that means divide by, not backslash, forward slash, I'm sorry. So A period forward slash, that means divide index operation by B, and indeed that you will have each index of A is divided by its corresponding index in B. Right? So this is a very powerful tool for us to have. Also, you can do addition, index addition. So let's say that we are going to have a vector E will equal to A added B. Oh, oh, I'm sorry. So index addition doesn't require the period. So we're going to say that E will equal to A plus B. And of course, it is clear here that when we do addition, we add the indexes by default. I'm sorry I made a mistake here, but when you do addition, you do addition on indexes by default. Right? That's the way we do addition with vectors to begin with. Another very important thing to learn with index operation is what we call the power. So let's define a new vector. For example, vector f will equal to a, and what you want to do is you want to make it to the power of 3. So here I'm going to have a period, and then I will have this sign to say the power, right? And then 3. So what that says is each index in A will be cubed. So each index in A will be cubed. The first index was 1. When you cube it is 1. The second index was 2. When you cube it is 8. The third index was 5. When you cube it is 125. So you can also use the power as index operation. That basically says each index in A is also have been applied to the power. And you can add different powers. It doesn't have to be 3 or 2. You can also use a floating point power. So let's say, for example, I will have let's say that I will have the vector h that will equal to a to the power of minus 4.7. And once again, you have used the powers on each element, and that's what you have. So that's all what I want to cover in vector operations at this moment. What we're going to do next is we are going to learn how to do functions. So we can apply functions to vectors. So this is a very important concept. And before we go forward with it, let us clear the window first, and then let me clear workspace, and let me clear the command history. And now what I'm going to do is I would like to how to get a function of a vector. So let me define a vector to be x will equal to, and I will start from 0 with an increment of 0.1, and this increment will end at value 10. So over here I have 100 index. So, and that's where you start to see the semicolon is handy. So if I didn't use the semicolon, I get 100 element or 101 element, right? So as you see, as I move forward, I get 101 element. So this is not good. What you need to do is you need to use the semicolon. So let me write x will equal to, will go from 0 to 0.1 to 10, and I will hit enter, and now I have 101 indexes for vector x. Now I want to say that y will equal to the cosine of x, and I'm going to add a semicolon because I don't want to repeat that. So what happened now is I apply a cosine function to each value inside X. So each index inside vector X, the computer will evaluate the cosine of that value at that index. And this is very powerful. See, so now I have an array that evaluates each value for X. So let me redefine X just for simplicity and say that X will go from 0 with an increment of 0.1, but this will go all the way to 0.5. This is just for simplicity, just to show you how it will echo. How will it echo on the computer? I will not add a semicolon, and now when I hit enter, I will have 6 values, 0, 0.1, 0.2, all the way to 0.5. Now I want to define y to equal to the cosine of x, and when I hit enter, it evaluates the cosine for each value of x. So each index in x will give me the corresponding cosine of that value, right? I can do the same thing with the sine of x if you want. I can do the exponential of x. Right? And then I can use a lot of other different functions as well. So this is very powerful. We can use all those functions that we learned in the elementary functions toolbox. So let me go back and refresh your memory with that particular toolbox. So if you write help lfun elementary functions lfun, this is one of the toolbox you should really master, as we said earlier. So if you hit enter, you will have a list of all those functions that you need to master. Remember, we said there is the trigonometric functions that you need to master. Most of them are familiar to most engineering students at the senior level or grad school level, where they know most of those trigonometric functions. You can also use the exponential functions, as I said here. So those exponential functions are also useful for most engineering students, especially the ones who study control. We can use the complex operations, and we can also use things like the rounding. Rounding and reminders become very important when we use DSP applications, because we have finite length words. So you have to always round the size of your number to 16 bits or 8 bits or 32 bits and so on. So they become very important when you implement algorithms on a DSP microprocessor. And that becomes very, very handy and very powerful for us. The bottom line, basically, or in summary, we are discussing the vectors. We said that the vectors are very powerful because you can declare them now as a sequential arrays, and then you can define functions for that sequential array. Let me clear the window one more time and show you a very interesting thing that we can do. Let's assume that t stands for time, and we're going to go from 0 with an increment of 0, 0, 1, and you will go for 10 seconds. So this is a very long array that roughly will have 10,000 points. I'm not going to echo it. It will be crazy for me to echo it. So I have to add a semicolon, and I'm going to hit enter. So now I define the time interval that will go from 1 second to 10 seconds with an increment that is 0.1. Right? And then what I want to do now is I will say that the output of the system will be 12.5 volts, for example, times E. You guys remember that E is exponential, of minus t over, let's say, 2, that's the time constant, right? Remember that? Times the cosine of 200t, right? So this is an exponentially decaying function and oscillating function. This is a very critical function for us in electrical engineering and most system engineering topics. Then I will add a semicolon here because I don't want to equal. I made a mistake. Okay, so what you do here is you need to make sure that this is an index multiplication. This is a very common mistake for us because this here is a scalar multiplied by a vector, and this one will give me a vector, so I have to make sure that vector times a vector is an index multiplication, right? So that's a very common mistake for students to have. I still made a mistake because there is a multiplication here as well. Okay, so now it's right. So what I have now is an exponentially decaying function, right? So let me just clear the workspace to make it look nicer, not the workspace, the command window, and let me just repeat the last statement. Okay. So this is an exponentially decaying function, and we said that t, if you remember, we defined t that will go from 1 to 10, and now I want to plot this function. So the way I would like to plot this function is I will use the command plot, and I will start with the x-axis, which is t, and this here, what it shows you is a help menu that reminds you how to use the plot function. So, you know, we don't need it, but focus on this line here. So you start with t, which is the x-axis, and the function, which is the y-axis, and now I will close. So you say plot the value of the x-axis, the value of the y-axis, and the close, and I'm gonna add a semicolon, and I will hit enter. So it will do the plot for us. Let me maximize the image for you so it's clear that this is an exponentially decaying function like shown here, and it is oscillating at a very fast frequency. This is a very interesting function. Now this figure window or the graph window will have their own menus. So basically you can open a new graph or save it. You can create a new, don't worry about that. And you can use the same thing you did here. You can edit and you can insert and you can do that. You can, for example, zoom. So let me zoom in this function, and I can move the zoom in function, you know, so you can play with it, you know. Let me just go toward the end. So you can see it's a sine wave that is exponentially decaying. Let me even zoom more and more, and then let's move forward. So it's a sine wave that's exponentially decaying as the time progresses. And this graph menu will have all options. You can print, you can save, you can open whatever you saved. You can also add stuff to it that we will give you the chance to learn how to use this menu in your own. So let me close it again, and let's do the plot so it gets you back to the original size. So basically what you do now is you can use the vector to define the index time, and then you can define the function that depends on your index, which is the time index, and now you can use that to plot a function just like I showed you here. So you were able to plot a function. Let's do another simpler example because this example is a little bit difficult. I already defined t, I already have t, I defined y. Let me define something I call y1, and y1 will equal to, let's say, 2 times the exponential of minus t. So this is a very simple function. It's exponentially decaying function, and now I want to plot it. So I will do plot. I will start with the x value, which is t, then y1, add a semicolon, and you can see that this is an exponentially decaying function that moves down. I can also add things to the graph, so let me try to minimize this a little bit so I can show you both the graph and the command window. So let me increase that. So here is my command window and here is the graph. Now what I want to do is I would like to add a label to the X label, and I want to call it time. So I wanted to add a label to the X label. So what I do is I will say X label, and then I will add a string, and the string starts with one quote mark, not two quotation mark, one quote mark. It's a little bit different than people who write programming in C. In C, the string uses double quotation mark. In Matlab uses single quotation mark. So what I will do is I will write time, and then I will end the string, and then I will close it, and when I hit enter here, you will see that the X label will have time in it. So let's see that when I hit enter. I'm gonna hit enter now, so observe that. You see it showed you the time here. So X label, the X label will show you the time here. Now I'm gonna write Y label in the command window, and the Y label does the same thing as the X label, but only on the Y axis. So if I want to label the Y axis, I will say Y label, then I open parenthesis, and then I will write a string, and I will say this is, for example, the voltage, close parenthesis, and then I will hit enter. So that's the voltage that I have, and you can see that the voltage here shows on the y-axis. There is another thing that I can add, which is called title, and title will give me the title of the graph. So you can see on the top of the graph here, I will have something called a title. So let me say that the title is going to be the time response. And you add that as a string again. So you open one quote mark and then you close the one quote mark. And when you hit enter, you're going to see that there will add a title here called the time response. So let me show you what happens when I hit enter. When I hit enter, you see it shows you the time response. So now I can create a graph, and this graph I can add X label, I can add Y label, and I can add the title of the graph. I can also add something called grid on. Grid on will turn the grid on, so when I hit enter, you will see a grid on the graph. See, so grid on adds a grid, and then I can say grid off. It will turn off the grid. So I can use grid to show the grid of the graph, which will make it easier to read. So this is a very powerful tool in terms of the graphs. Graphs is one of the most important things that we use in Matlab, because the mathematics tend to be complex. We don't understand it. We don't interpret it as nice as graphs. Engineers are really good at interpreting the graphs to give us a better understanding of the behavior of the system. So a very important tool for us to have is to be able to plot the functions. So when we come back, we will learn how to do scripts and how to do functions and how to do matrices.